A graph is a set of vertices and set of edges that connect them together. Now, having this definition, the question is how to represent this in C++. And we want to represent a graph in C++ because real-life problems map to graphs and we want to solve them systematically. Basically, we want to run algorithms like DFS, BFS, shortest path, and others. I start this talk with a very quick crash course on what a graph is. Then we talk about how to represent a graph using STL standard template library in C++ and what kind of data structures we should use. And also for each data structure, I will show an implementation of a simple algorithm. What is a graph? The mathematical definition of a graph is that it has two sets, one set of vertices, also known as nodes, and one set of edges. Now, the graph itself is a tuple whose first item is V, the set of vertices, and the second item is a set of edges. So a graph is a tuple or it's a pair. Each edge is between two nodes and it can be undirected or directed. If the direction matters, the edge is an ordered pair. If it doesn't matter, the edge is an unordered pair. Now, having this definition, how do we represent this in C++? And the question comes down to how do we represent sets, meaning a collection of items, and pairs for representing edges. Here we see how we represent this graph in math, which is the set V of vertices 0, 1, 2, 3, and E is the set of edges between 0, 1, 1, 2, 2, 3, and 3 and 4. So now if it's undirected, this order doesn't matter, otherwise the order matters. And one last definition is that if there's an edge between two nodes or two vertices, we call them to be adjacent or neighbors. A very classic problem in graph theory is called the 7 bridges of Konigsberg. Konigsberg is a city in Russia which has a river, and the river has 7 bridges, and people were wondering if they could go from one section of the city to another, crossing these bridges exactly once. So the requirement was to cross each bridge exactly once without ever going back and without ever crossing each bridge more than once. So for example, I go from here to here, cross this bridge, then cross this bridge, then cross this bridge, then cross this one, then this one, and this one. But in order to cross this last one, I have to cross one of these two bridges at least one more time to be able to cross this. The question was, can we cross all of these bridges exactly once without ever going back or cross each bridge more than once? Euler was a mathematician that tried to solve this problem, and in order to do that, he abstracted this problem to something that today we know as a graph. So each landmass was mapped to a node or a vertex, and each bridge was mapped to an edge, what we know today as an edge. So for example, now between 0 and 1, there are 2 bridges which are represented like this. For each vertex, Euler defined a number called degree, which was the number of edges that touch each node. For example, the degree of this node is 2 because we have 2 edges touching node 0. We have 2 edges touching node 1. For 2, the degree is 2. For 3, the degree is 2. And then he observed that with the requirements that we had, never go back and cross all the bridges, the graph should have exactly 0 or 2 vertices with odd degree. Euler observed that in order for the graph to be Eulerian, meaning we can cover or cross all of the bridges exactly once without ever going back or disconnecting the pen and paper, the graph should have exactly 0 or 2 vertices with an odd degree. For example, this graph has 4 vertices. All of them have degree of even. That means it has 0 vertices with odd degree. That means the graph is Eulerian. Now this one, it has 4 nodes with degree of 3. So it has 4 nodes with odd degrees. And that means this graph is not Eulerian. Now using these definitions and reminders, how do we represent a graph in C++? There are basically 3 methods. Method 1 is the direct translation of the definition, basically representing two sets. Set 1 is V, set 2 is E. The second option is something that's called adjacency list. Don't get scared by its name yet, it's very simple. And then the third one is adjacency matrix. Now, before I go through the details of each method, remember that what you want to take away from each method is to be able to learn how to initialize a graph using each of these methods and data structures, and then how to run a simple algorithm. So this is what you want to take away from this talk. All right, the direct translation of the definition. So we said we have two sets. Now, in order to represent a set, which is a collection of items in C++, you can use STL's standard template libraries vector or linked list or set to represent V. For E, you could represent again a set using a vector, a list, or a set. And then for each pair inside E, you can use std pair or a vector of size 2 or a list of size 2 or a set of size 2. So these are all the options that we have. For simplicity, let's pick vector and pair. You could choose any of other options. I will talk about the differences. There are minor trade-offs and differences. I will talk about them later. But let's start with something simple. Now that we picked these options, your graph can be a simple class that has one vector representing the vertices, one vector whose items are pairs of integers representing your edges. Your constructor takes two parameters, V and E, and initializes your member variables using the input parameters. And then we define a new function or a method that checks to see if this graph is Eulerian. The first thing that I promised was to describe how to initialize the graph. STL has a feature called uniform initialization, which allows any container to be initialized using these curly braces. So for example, a vertex can be initialized using these curly braces, which completely matches our mathematical definition. And similarly, your E is a set of pairs. Again, each pair is initialized using uniform initialization. That means I have a pair of 0 and 1 and pair of 1 and 2 and so forth. So you see there's a really nice one-to-one correspondence between our implementation and their mathematical definition. Once you define V and E, you can simply pass them to the constructor and construct your graph, and then call this function to find out if a graph is Eulerian or not. Let's see what's the details of this function. In order to see if a graph is Eulerian, you should answer this question. Is the count of odd degree vertices exactly 0 or exactly 2? So the algorithm comes down to finding the degree of each node and then find out how many odd degrees we have. In order to find the degree of each node, we have to iterate through our edges. So let's first define a table representing the degree of each node. So I have 4 nodes. I define a table of 4 items. I initialize them to 0. This is done using defining a vector and having the size of the vector to be exactly the size of V. And we know that in STL, as you define a vector, it will initialize them by default to 0. Having this, then you can go through your edges, iterate them, and then as you see your edges, because they are pairs, you add 1 to the degree of the first item, which is the start, and then the second item, which is the end of the edge. Once you do this, you can simply run through this table, iterate through the degrees, and then count the number of odd ones, and then simply return if the counter was 0 or 2. And that's a very simple implementation of finding a graph, if a graph is Eulerian or not, using this data structure, which is the direct translation of our definition. This representation could be more compact by dropping V. So basically, the idea is if I have my edges and I know the degree of each edge is at least 1, I could drop V and just represent the entire graph only by its edges. So if I give you this and I just tell you I have one set of edges, you could go and iterate E and then deduce what the vertices where. So you could say, okay, I go through E, I see one vertex to be 0, there's a 1, I've seen 1 before, so there's a vertex 2, and so forth. You can do this if you know that each vertex is at least connected to one edge. So you probably want to do this maybe only when you're concerned about the size of the problem. Otherwise, it's more convenient to have both V and E together. Method number 2 is called adjacency list. So in adjacency list, rather than having two sets for vertices and nodes, we have a table and there's a mapping between each node to its adjacent. For example, node 0 is mapped to its adjacents 1 and 2. And node 1 is mapped to its adjacents 0, 2, 3, and 4. So we can do this for all of the vertices and create this table. Now the question is, how do we implement this in C++? How do we model this in C++? So one way to do this is to create a new class that represents one row of this table. So let's call this new class to be vertex that has two items, two members, one a vertex number and one a list or a collection of adjacents. With this idea, the definition would be very simple. So defining the class vertex or structure of vertex, which has a vertex number, it's an integer, and a set of adjacents. So again, for the set, we could have used a list or a vector. We just picked adjacents to be a set. You have other options and you can use them. I will talk about the differences later. Now, having this definition, your graph is nothing but a list of these vertices. Again, a list can be represented by STL's vector or STL linked list or STL set. Here we picked vector. Again, there are minor differences. Let's talk about them later. So now your vertex constructor takes two inputs for vertex number and adjacent list, and your graph takes a vector of vertices as its input. With this, initialization is very simple. You can just define, using uniform initialization again, you can just define new vector using these curly braces, and then each item in the vector is a vertex that has V. So here 0 is the V, and 1 and 2 is mapped to this set. So again, you can see there's a really nice mapping between our table and how we initialize our graph. Now, having this class defined, how do we modify this function to find out if the graph is Eulerian or not? So again, if you remember, we have to find the degree of each node. So having this definition of classes, the degree of this node is actually really ready. So we already have it, which is the length of these lists or sets. So all you need to do is to go over these rows, iterate through your V, and then for each node, the degree would be the adjacent size. So we use the size from STL to just get the degree. The rest is like before, we just count how many odd degrees we had, and then we report it to be 0 or 2. Rather than defining a new class for each row, we could go ahead from the beginning and say our graph is nothing but a map using STL's map of an integer to a set of integers. It is a map of an integer, which is a vertex number, to a set of integers. Again, this set could have been a vector or a list. We just picked the set. So the initialization is very straightforward. Each item in the map is a pair whose first element is an integer, whose second element is a set of adjacent values. So there you have it. This was an alternative way of implementing a graph using adjacency list. All right, the third method is adjacency matrix. Adjacency matrix is a two-dimensional matrix or table that shows what nodes are connected to each other. So each row represents a node, each column represents a node, and then if there's one in one entry of the table, that means between these two nodes there's an edge. For example, between 0 and 1 there's an edge, so we represent them by 1. Between 0 and 3 there's no edge, so 0 to 3 should be 0. If the graph is directed, the matrix doesn't have to be symmetrical, but if the graph is undirected, then the table would be symmetrical. That means if there's an edge between 0 and 1, there has to be an edge between 1 and 0 as well. As soon as I show you this, you should be concerned about the memory cost, because for a graph of size n being the size of the nodes, you will have a matrix of size n to the power of 2. So the size is the big concern for adjacency matrix. Now let's see how do we implement this in C++. So your graph is nothing but a vector of vector. A two-dimensional vector, two-dimensional matrix is implemented by a vector of a vector, and we call that adjacency. Your constructor takes that vector of vector as an input and then initializes your adjacency. You can see we can use uniform initialization again to initialize our graph. So again, this matches really well with our initial table. And then your graph can call the constructor, pass this two-dimensional vector, and you are done. Now let's see how we can modify the is Euler walkable function to see if the graph is Eulerian or not. Again, we define our table of degrees. So now, in order to find the degree of each node, all I need to do is walk through each row and count the number of ones. So in this row, 0 goes to 1 and 2. That means the degree of 0 is 2. To do that, I have two for loops. One goes through the rows, one through the columns, and then each time I see a 1, I add 1 to the row number. That's what we do here. If we see the adjacency of I and j being our indices of the for loops, if it's 1, then you can simply add to the degree of your row number. And then the rest is the same. So what should you take away from this talk? What is the summary of this talk? So we introduced 3 methods of representing graphs in C++. The direct translation of the definition, 2 sets, one for vertices, one for edges, or adjacency list for each node, or an adjacency matrix. So let's compare all these 3 methods. If you just want to iterate through edges, in this method, you have to go through the entire list and iterate them. So that would take O of m, m being the number of edges. In the adjacency list, you have to go through the entire table. So there are n rows, n the number of vertices, and then there are a maximum of m items. So that means the entire iteration would take m plus n. Slightly worse, but still not too bad. For adjacency matrix, you have to go through the entire matrix, so that would take O of n to the power of 2, which has the worst one. Now, if I give you node I and I ask you what are its adjacents, in this method, you have to go through the entire list again. That would take O of m. But for adjacency list, you already have it ready, so that would take O of 1. For adjacency matrix, you have to go through one row, so that would take O of n. If you want to check if I and j are adjacent, you have to check to see if the pair I and j or j or I exist in this list. So that means you have to iterate through this vector and see if you can find it. If it was a set though, searching inside a set takes O of log m. So that means you can see what would be the difference between picking a set or a vector for your E. For adjacency list, if you want to see I and j are adjacent, for I, you can quickly find it in constant time. For j, you have to go through this list, which would take O of log n if it was a set, or O of n if it was a vector or a list. In adjacency matrix, though, you could quickly check the location I and j and see if it was 1 or 0. So that means it takes constant time. So this has pretty fast speed. How to calculate the degree of each vertex? In this method, you have to again go through the entire list as we saw. So that would take O of m. In this other method, we already have the list. So just check the size of the list using STL size would give us the answer. So that would be constant O of 1. In adjacency matrix, we have to go through the entire row. So that would be O of n. And then the memory size for this method would be m plus n, n being the number of nodes and number of edges. For adjacency list, also n plus n, and an adjacency matrix has the worst one, which is n to the power of 2. We already saw some differences between vector and set, but let's look at this more closely. Remember that in STL, a set is automatically sorted, and insert, delete, or find would take O of log of n, n being the number of items in the set. An unordered set, on the other hand, is not sorted, and insert, delete, or find will take O of 1 amortized. If you don't know what amortized is, you can watch my video on amortized analysis. It's not that important for this talk. Rather than set or unordered set, if you go with vector or a list, a vector is not sorted. Insert, delete, or search would take O of n. If you just want to push something at the end of the vector, that would take order of 1 amortized. A list also is not sorted. To find something and then delete or insert, that would take O of n. But if you know where exactly you want to insert or delete, unlike the vector, that would take O of 1. So that means depending based on these numbers of complexities, so you may want to go with a set if you want to, for example, keep your nodes sorted, but you may want to go with unordered set if you don't want to keep them sorted, but the speed of find and delete or insert is more important to you. Beside the differences between the complexity, the time complexity, there's one more important difference, which is if you want to represent something that's called a graph, which we just saw, or something that's called a multigraph. A multigraph is simply an extension of a graph, but between two nodes, there can be multiple edges. And this is what we saw in the original Konigsberg Euler's problem. There were multiple bridges between two nodes. Now, if you pick a set or unordered set, you cannot represent a multigraph because a set cannot have a repetitive item. Therefore, if you want to represent or implement an algorithm that runs on multigraphs, you have to pick a vector or a list. That's it, guys. Thanks a lot for watching my video. Please make sure to subscribe and like the video, and I hope to see you in the next one.